have nonmetals, and they want to do this transferring because metals have very few valence electrons, nonmetals have a lot. So it's really easy to take and transfer the metals directly to the nonmetals. But what happens when you have two nonmetals that have either the same or very similar numbers of valence electrons? If that's the case, then they can't transfer. They're going to end up having to share. So one example is how hydrogen forms a diatomic element, H2. So hydrogen, if you look on the periodic table, you see that hydrogen has one valence electron. Remember, if it has two, it'll make it like helium, because helium is number 2 and it's a noble gas. Remember that first energy level only holds 2? So the purple hydrogen cannot pull the red hydrogen's electron away, or vice versa, because they have the same pull. They both want each other's electrons. The only way they can form a stable molecule is instead of transferring and forming ions, they're going to share. Sharing valence electrons is what creates what they call covalent bonds. Covalent bonds are very stable bonds that help to form and link atoms together. So what ends up happening is this hydrogen, the red hydrogen, gets close enough to the purple hydrogen so that their electrons are basically held between. So that means that these electrons, they go back and forth. The electrons now, they kind of have like two atoms to span back between. So they go from the purple hydrogen to the red one, to the purple to the red. So this means now the purple hydrogen can act like it has two. It acts like it's like a noble gas. Same thing with the red hydrogen. So the red hydrogen now can act like it has two, and that creates this stability. So because those two electrons are now being shared, they call this a single covalent bond. They can use the Lewis structure, where they use just a line to indicate that pair of electrons. So I'm sure you've seen molecules just with like a line between two atoms. That means that it's a single pair of electrons that's being shared. So hydrogen does this, chlorine, fluorine, bromine, iodine. They all exist in nature as Cl2, F2, Br2, and I2. So you don't just see a bromine atom. You'll see bromine existing as what they call diatomic, which means two. They call them diatomic elements. And all of these, chlorine, 1, 2, 3, 4, 5, 6, 7, right? So chlorine has 7 valence electrons. If you look, it's at the top of group 7. So this chlorine and this chlorine share a pair of electrons between them. And do you see that now each one of them has 8? So that creates this stability. Chlorine does this, bromine does this, iodine does this, fluorine. They only form a single bond, single covalent bond, because they have 7. If they share one electron with another atom, that's going to create stability. So you will see the chlorine with this dash to another chlorine. Now these electrons, the electrons that are around the chlorine, but they're not part of the bond, they call these non-bonding. These are non-bonding electron pairs. These electrons, they belong to the chlorine. They're not shared. So hence the name non-bonding, because they don't form bonds. But do you see that they give chlorine their 8? So chlorine's got one line, which is 2 electrons, plus 6 around its outside. So now it has its total 8. And same thing with the other one. So you would see the same thing with fluorine and bromine and iodine, is that the fluorine would form a single covalent bond with another fluorine, 7 and 7, but that shared pair in between is what creates the bond. But these fluorines have non-bonding electrons. They're only sharing one pair. So out of nonmetals, Nonmetals and hydrogens are the only ones that do this. Metals do not form covalent bonds. Only nonmetals and hydrogen. So we've actually already just named five of the nonmetals, and they only ever form single bonds. So fluorine will only ever have a single bond. Chlorine, bromine, iodine, and hydrogen. They will only form a single pair, a single covalent bond. So if you look at the periodic table, that only leaves what? Right, so we took care of hydrogen, and we took care of all of group 7. So it really only then, the nonmetals that are left are the ones that are in groups 4, 5, and 6. So that means now we just about carbon, nitrogen, phosphorus, oxygen, and sulfur.
Okay, so on this, on the printout that I did, it already has nitrogen and oxygen, so are those like not in that?
They're in there too, yeah, so those are the other ones. So here shows like how chlorine shows 2 chlorine atoms forming a single covalent bond. Right, so you can see the dash. Sometimes they call the electrons that don't form any, that belong to the chlorine, the lone electrons or non-bonding electrons. Those are the 2 terms you might see referring to the electrons that are not part of a covalent bond that belong to a specific atom. But now we're looking at these. And in fact, these are the ones that we really end up spending time on. So, and there's just these 5. There's carbon, nitrogen, oxygen, phosphorus, and sulfur. So do you see that carbon's in group 4? Carbon's in group 4A. Nitrogen and phosphorus are in group 5A. Oxygen and sulfur are in the group 6A. So it's really just these 5. So carbon has 4 valence electrons. So in order to be stable, it has to have how many? 4 more, right? It's going to end up having to have 8. So carbon, it has 4 valence electrons. So the only way that carbon can be stable is to have 8. So it is going to have 4 bonds. It's going to have to form 4 covalent bonds, and that will give it the octet. So 4 valence electrons form 4 shared pairs with other atoms in order to create that stability. What about nitrogen? Yeah, nitrogen. Right. So nitrogen has 5, right? 5 valence electrons. It's in group 5A. So I know that it is going to need 3 covalent bonds, because it's going to need the octet. So you're going to end up having to form pairs. Any electrons that are not paired are going to have to form covalent bonds to become stable. Well, carbon doesn't just have to form 4 single shared pairs of electrons. Carbon can actually form more than 1 bond with other atoms. The goal, though, is just to make sure it has a total of 4. So do you see in this one how carbon has 4 single bonds? So those would be 4 individual bonds. But then, in fact, carbon can form what's called a double bond. A double bond is where you have 2 pairs of electrons, or a total of 4 electrons shared between carbon and another atom in order to create stability. In fact, it's even possible, not that common, but it is possible for carbon to even form a triple bond, because that would be 3 pairs of electrons, and then 1 more pair of electrons would give it its total of 8. So do you notice around carbon, you'll always have 4 lines? Okay, there's always 4 lines, and there's never non-bonding electrons. Carbon always uses its electrons to form bonded pairs. Nitrogen, looking at nitrogen, and in the fact this would be phosphorus as well, because phosphorus can do this, but nitrogen, notice that nitrogen can form 3 covalent bonds. So N can have 3 lines attached in any combination. You could have 3 single bonds, like the top one. You could have a double bond and a single bond, or you could even just have a single triple bond. So when you look at this, do you see that in all of these combinations, nitrogen has 1 pair of electrons that are non-bonding that belong to the nitrogen, and it's going to share 3 pairs of electrons in some combination. Phosphorus can do the same thing. So phosphorus could end up with 3 singles, or phosphorus could end up with a double and a single, or phosphorus could even end up with a triple. Oxygen's the only, and sulfur are the other group, group 6. So you know that means that they've got 6 electrons. That means they've got to form 2 bonds. So notice oxygen can form 2 single bonds, or oxygen can form a double bond, but that's the max. Oxygen can't form a triple bond because it only has the ability to share 2 pairs of electrons in order to become stable and have its 8. So carbon's got to have some combination of 4. Nitrogen's going to have some combination of 3. Oxygen's going to have some combination of 2, either 2 singles or 1 double. But that's the maximum. Same thing with sulfur. So sulfur can have a double or 2 singles because it's in group 6. So here's their example. The example for this one is CH4. And so in this is a little bit different than ionic in that I'm not going to give you like random numbers of them. You will always get a formula. In fact, the formula that I'm giving you, these examples are really the most common ones. They're pretty simple. We're not going to make them any more complicated than this. But in this, I have CH4. So the formula tells you exactly the number of atoms in the molecule. So you don't have to figure it out. Covalent molecules, the formula tells you the exact number of atoms. I don't have to do any charge swapping or anything like that. The formula tells me how many. So CH4 tells me that I have 1 carbon and I have 4 hydrogens. So the rules, what I do is I list the atoms. I list how many electrons and how many bonds each of them needs. So for carbon with 4 hydrogens, I have 1 carbon and I have 4 hydrogens. So that's the formula. Carbon, I know, has 4 electrons and needs 4 bonds to make 8. Hydrogen has 1 electron, and hydrogen only needs 1 more electron to have 2. Because remember, that makes it like helium. So just remember, hydrogen's kind of the oddball that way. Hydrogen never forms more than a single bond. So then the second step, I'm always start with the atom that needs the most bonds. So when I look at carbon versus hydrogen, carbon needs 4 bonds, so I'm always going to start with that first. So whichever atom needs the most bonds, you always put it down, and I say like make it the center. So the atom that needs the most bonds is always going to end up in the middle. And you're going to put things around it to try and create the stable octet. So I'd put the carbon with 1, 2, 3, 4. Then I'm going, can you see that I need 4 pairs? I need to share 4 electrons, and I have 4 hydrogens. So by putting 1 hydrogen at each of the electrons, pairing them with the carbon, then that's going to put a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. So remember, like with those valence electrons, you never end up with more than 2 up, 2 down, 2 left, 2 right. Those form those single covalent bonds. And then I could take this and swap it into the line structure or the Lewis structure, where it's just a carbon in the middle with 4 single bonds, a hydrogen attached to each. You can see that hydrogens all have 2 in this. And then the carbon has 8. Mm-hmm. Carbon doesn't have non-bonding electrons. Carbon has 4 electrons, and every single electron forms some kind of covalent bond. Same thing with hydrogen. There's no non-bonding electrons because hydrogen, when it has 2 electrons, that makes it like helium. So that's all it needs. So you won't have now nitrogen, oxygen, sulfur, and phosphorus, they have non-bonding electrons. And then the halogens, the chlorine, fluorine, bromine, and iodine, they have those non-bonding electrons are the electrons that belong to an atom and don't form a link to another one. All right? So, steps. So we did this one, right? So we ended up with this. Carbon with 4 single bonds to the hydrogen. So what about NH3? So NH3, how many, when you look at nitrogen and 3 hydrogens, nitrogen has how many electrons? Total, but how many electrons in its valence shell? Because remember, that's really what you want to know. That's the group. So the number of electrons in the outer shell is always its group number. So nitrogen has 5 electrons. Hydrogen's in group 1, so I know hydrogen has 1 each. Hydrogen never needs more than 1 bond. But nitrogen needs have a total of 8, so how many bonds will it need to form? 3. So do you see that with 5 valence electrons, I need 3 bonds to equal 8? So the number of valence electrons, which is the group number, plus the number of bonds has to equal 8. So I list them. Now I'm going to start with the atom that needs the most bonds. So in this one, which one needs the most, nitrogens or hydrogens? So I'm going to put the nitrogen down first, N, dot, 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 right? So there's the 5 electrons. And remember to spread these out. You may have to move them around, but spread them out. Now, I've got to add 3 hydrogens. So where will I add the hydrogens? Yep. So I'm going to add a hydrogen here and form a single bond. Add a hydrogen here, form a single bond. Add a hydrogen down at the bottom, and a single bond. You see in doing this, now you can see that nitrogen has 8 around it, 2 up, 2 down, 2 left, 2 right, and each hydrogen has 2. I've used all the atoms. NH3 is a nitrogen with 3 hydrogens covalently bound or single bonded to it. And if I was going to do the Lewis structure, I would just have a little dash to each H. So H2O, formula, hydrogen, hydrogen, oxygen from the formula. I told you, you will use the exact formula. You don't have to figure out the formula. You'd always have the exact formula. So I know that hydrogens are 1 electron, and how many bonds? 1, right? Because they just want 1. They only need 1 bond to be like helium. So I will tell you, hydrogens are never the center. They're always around the outside because there's only a single bond to them. So they always kind of get added at the end. But oxygen has how many? 6. That means it needs how many to make 8? 2 bonds. So that tells me which one to start with. I start with oxygen with 1, 2, 3, 4, 5, 6. And remember, it doesn't matter where your dots are. You should just make sure you spread them out. So you should have 2 dots on 2 sides, single dots on 2 sides. I don't care where they are. So it would be completely fine if you decided that you wanted to have it like that. That's fine, okay? The key thing is that you are only going to end up with 2 pairs on one side of the oxygen and 2 singles on 2 sides of the oxygen. So now I can see that I've got to add my hydrogen, so where do they go? Yep, wherever the singles are is where you're going to form the covalent bond. Covalent bond, H. So wherever your single electrons are around the oxygen is where you add the hydrogen and form a pair. So I've got like 1 purple dot and 1 blue dot. So that represents that covalent bond. And if I switch this to the Lewis structure, I have that. Would it be fine if I had this okay? And if you remember in lab last week, like you could build this and kind of flip it around and make it look different, but as long as you have an oxygen with 2 pairs of non-bonding electrons and then 2 lines, 1 to each hydrogen, then it's right. They might be up above and below or left and right, or they might make like an L. All of those would be fine. Same thing with this ammonia, NH3. If I had my 2 dots here, this is correct, okay? So you could have your 2 dots on any side. The other 3 sides have a single dash to a hydrogen. So those would be fine too. So don't get like hung up that like, oh, it doesn't look exactly the way it, I've drawn it. As long as you could like take this molecule, like flip it around, like think like, okay, if I just rotated it a little, it would look just like hers. That would be fine. So now we know oxygen exists as O2. If you give a patient oxygen gas, you give them O2. You don't just give them O. Well, oxygen has 6 valence electrons, and how many bonds does oxygen need to be stable? 2, because remember that means 6 electrons plus 2 bonds is going to make there 8. So if it's only O2, I know I only have 2 oxygens to use. So if I start off with 1, 2, 3, 4, 5, 6, and like I said, doesn't matter how you like write them out, but 2 sides of the oxygen should have 2 electrons, 2 sides of the oxygen should have a single electron. If I add an oxygen to it, 1, 2, 3, 4, 5, and 6. So see where I've done my pairing? Well, O2, I'm done. Now I've got 6 purple dots, I've got 6 green dots, I've put down all the electrons, I'm done. But when you look at it, can you see that they're not stable? They don't both have 8 around them. The purple oxygen has 7, the green oxygen has 7. So this is like at the last resort, this tells you that you've got to make a multiple bond. So you're going to have to make a double bond in order to be able to create this stability. So see these electrons that don't have a pair. These are going to move between the 2 oxygens. So this one is going to move here, and the purple one is going to move here. So you see there's still the purple dots are still around the purple oxygen. The green oxygen dots are still around the green oxygen. So I didn't like just move them over. I didn't take the green ones and put them over on the purple side. They're like in between, or they belong to the green oxygen themselves. But this now creates, you see 8? 6 and 2, and then if I do the same thing, do you see 8? 6 and 2. So that is a double bond. That is a double covalent bond. 2 pairs of electrons are being shared. So you would write this out with 2 dashes. Each oxygen would also have how many non-bonding electrons? 4. Do they have to be at the top and on the outside? No, but they can't be in the space between them. They've got to be around like the outside. So you can put 2 above and 2 on the outside, or you can put 2 on the outside and 2 on the bottom. I don't care. But they can't be in between, because if they're in between, they're sharing. And those purple dots that I've got in that Lewis structure represent electrons that belong to the atom, each oxygen atom, and they're not shared. The lines are the ones that are shared. But you always do double bonds, triple bonds last. Don't try to do them first, because you may not need it, okay? First thing to do is always get all your atoms down. Then, if you need to, you can form multiple bonds. So like, for example, carbon dioxide. So carbon dioxide, carbon has 4 electrons, which means 4 bonds, right? So it's in group 4. Oxygen, we said, has 6 electrons. That means 2 bonds, right? Because we were trying to make 8. So 6 electrons, 2 bonds. So when I start this, which do I put down first? Put down carbon first. Not just because carbon is the first in the formula, but because carbon needs the most bonds. So now I've got to add an oxygen, and it really doesn't matter which one because they're the same. So I could pick any of these dots to put in oxygen. So I could put it up here. Okay? So I put a red oxygen with 6 dots. 1 dot forms a single bond. Okay? So now I've used 1 oxygen. Now I got to add the other one. So I'll do green. And it doesn't matter where I add it. I could add it here. 1, 2, 3, 4, 5, 6. So someone said, well, why didn't you add the green oxygen to the red oxygen? Right? How do you know that you need to add that green oxygen to the purple carbon? So my answer to that is, anytime I add an atom, I always add to the atom in the molecule that still needs the most bonds. So if you look, before I put this down, how many bonds does the carbon need? Like how many dots don't have pairs? 3. Can you see that? There's 3 dots without pairs. But oxygen, the red oxygen, how many pairs does it have that don't have a match? Just a single electron. That's only got 1 single. So because of that, that's how I know I've got to put the oxygen on the carbon. Because the carbon needs the most bonds. See if I go back to my color. There. 1, 2, 3, 4, 5. Okay? But now I've done all of it. So now if I put all my electrons, all my atoms are down, now I know I have to form double bonds. So the red oxygen, if I want to form a double bond, the red oxygen is going to form a double bond with what? With the carbon. And I'm going to take and move that red electron and one of the purple electrons between the oxygen and the carbon, the red oxygen and the carbon. So I'm going to move this one. So this one is going to go here. And then I'm going to change and put the purple. Oh, I just erased all that. And put it here. There's not much space between. See if I can make, so now I got 2. My O is still here. 1, 2, 3, 4, 5, 6. Okay? So I made a double bond. So notice that all the red dots are between, either on oxygen or between the red oxygen and the carbon. So I didn't take like red oxygen electrons and put them over on the green oxygen. I kept them. So they're always still going to be like connected to their atom they belong to. So, but then, do you see that carbon and oxygen, the green oxygen and the purple carbon, see this one right here and this one right here. See how those are not paired? So those are still like floating about. Well, they're going to pair off, and they'll do that by moving between the green oxygen and the purple carbon. So I'll end up with a dot here. That moves this one. And then I'm going to move this purple one between. So when you get done, you should still have, the green oxygen should still have all of its electrons like connected to it. The red oxygen should still have all of its red electrons connected, and same thing with the carbon, but they're sharing pairs to create the stability. So if I was going to take and do the Lewis structures to this, I would have this. 2 dashes between the carbon and the oxygen on either side. It would be fine if you wrote it out like this. It would be fine if you wrote it out like this, straight across. We'll talk about geometry in the next class, like why. Okay, so between now and next time, there is N2, so you can do the structure, try to do the structure for N2. There is CH2O and then HCN. So see if you can do those 3. We'll do those ones, and then we're going to talk about like what is shape, why is shape important, talk about polarity, and then the naming. So naming of covalent bonds is a little different than the naming that you've got for the ionic ones. Okay, so we'll talk about naming next time too. So now I've got all of these, right? So now I've got them finished, and I need to just use the ones that I've got. I can't add any more dots. I can't add any extra hydrogens, carbons, or nitrogens because I've already got them all down. So this is the point where you know you got to form a multiple bond. So I know I can't form multiple bonds with hydrogen because hydrogen only ever ends up with one bond. So the only option is to form a multiple bond between what? Yeah, between carbon and nitrogen. So carbon and nitrogen are the only ones that can end up having multiple bonds. So now I go in and I'm going to just move. I'm going to move this nitrogen dot. Oh, it's not going to let me move that one. I'm going to take that one away and move it over here. I'm going to move the carbon, which is black. I'm going to take this one away and move it over here. And then I'm going to do the same thing, but I'm going to do it with these ones on the top. They won't let me erase them. Move this one into the middle and move this one into the middle. Okay, so the ones that I scratched out, they should be gone. I just can't erase them unless I close this too. So this leaves me with a nitrogen with 3 dots, 2 up here. There's its 5, and it's connected to a carbon. The carbon has 3 of its electrons shared with the nitrogen, and the last electron is the one that is shared with the hydrogen. So when I have those 3 pairs of dots, when I transfer this to a Lewis structure, I would have a triple bond. Okay? So I'd have H dash C, then dash 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 with an N. And it doesn't matter where those non-bonding electrons of nitrogen, you could put them above the nitrogen, to the right of the nitrogen, below the nitrogen. As long as they're connected to the nitrogen, that's fine. It's hydrogen cyanide. Okay? Honestly, these are the ones to practice. These are the ones, if I ask you to draw any on an exam, these are going to be the ones that I'm going to ask you to draw. I'm not going to give you like great big huge ones. We'll wait till next chapter for those. But for just the simple ones, it will be these ones. So we talked about naming ionic. So remember that when just generally naming ionic molecules, remember you use the whole name of the metal, first part of the nonmetal, and then you add IDE. Unless it's a transition, you got to use the Roman numerals. Unless it's a polyatomic, in which case you got to use that. Right? But sort of the first part of the nonmetal plus IDE. So that's kind of like the basic plan with ionic. Covalent's a little different if you're talking about what they call binary compounds. Binary just means 2. So they found, hey, we have H2O. That's a covalent molecule because it's nothing but hydrogens and nonmetals. But wait, you can also have this. Wait, how do you name that? Okay, so if the first one is a hydrogen with 2 oxygens, but because we're talking about sharing electrons, we can also have a molecule that has 2 hydrogens and 2 oxygens. You can't have that with ionic. With ionic, NaCl, that's the only way it combines. One sodium and 1 chlorine. So the formula would only be NaCl, so the name is just sodium chloride. But here, water, H2O2, could be like this, right? So you've drawn that one, so you remember that one. But I could actually have an oxygen linked to another oxygen, linked to a hydrogen, linked to a hydrogen. So can you see how that could happen? Because oxygen has the ability to have 2 covalent bonds. Do you see each oxygen has 2? Hydrogen has a single. So can you see how those can exist? Because we're sharing, not transferring. So we can get much more complicated in our arrangements and structures with covalent than we can with ionic. So they said, okay, because of that, you have to indicate the number of each element in the formula by using number prefixes. So the number prefixes are these. You won't see these very often, but I will tell you through 10. Okay, so 1, they always use the term mono. 2, di. 3, tri. Those ones aren't too bad, okay? But 4 is tetra, okay? Instead of quad, it's tetra. And the way that I remembered this when I learned this is because, do you remember the game Tetris? Do you remember the little game where the blocks dropped? And it was either a little square of 4 or 4 blocks in a row or 3 and then a turn like an L. So that's where the name came from, because tetra means 4. So they were just ways of arranging blocks of 4. So tetra means 4. But then from there, do you see those look like geometric shapes? Like a pentagon is 5-sided. A hexagon is 6-sided. Heptagon is 7. Octagon is 8. Nona is 9. Deca would be 10. So from here forward, it's really just geometrical shapes. They really match. So you've really kind of got to learn to remember 1 is mono, 2 is di, 3 is tri. Most people remember those okay. But then that 4 one is kind of strange. It's a tetra. So now, whole name of the first element, first part of the second element plus IDE. So do you see the part I wrote in red at the top? Do you see how that sounds just like ionic? Sodium chloride. Whole name of the first element, first part of the second element plus IDE. So that part's exactly the same. But I've got to use a number prefix to indicate the number of the first element and a number prefix to indicate the number of the second element. The only exception, I do not have to use mono if the first element is a 1. If the second element is a 1, then I do have to use it. So if I have NO, what would I call this? So N, whole name of the first element, so that is nitrogen. I do not have to put mono because it's 1, but I do for the oxygen, so that would be what? Yep, so when it's monoxide, you shrink the O's, like you only use 1 O, so you call it monoxide. So what's the second? What's N2O? If there's 2 nitrogens, then I have to use di. Still use the whole name of nitrogen because it's the first element, so dinitrogen. And since there's only 1 O, I would still use, yep, it's a monoxide. Dinitrogen monoxide. Crazy? Okay, what is then NO2? What is N? Nitrogen. And then O2 would be, yeah, dioxide. What if I had N2O4? 2 N's. Always use the full name of the first element. Then, what's 4? So when you have vowels come together like mono-oxide, you drop the O of mono. Same thing here. If you have the 2 vowels like tetraoxide, you would just drop the A and it'd be tetroxide. I won't mark it wrong if you forget to drop it. I don't really care that much. But if you're answering questions in your homework, if you have 2 vowels, then they get dropped. The prefix number vowel gets dropped off. So like if you had pent and oxide, it would be pentoxide, no A. If you had oct and oxide, it would be just octoxide. Sounds really strange, but all right. So by this, what is CO2? It's one that's pretty familiar to everybody, but that's why they call this, yep, carbon dioxide. So carbon dioxide means 1 carbon, 2 oxygens. So if the first element only has a 1, you don't have to use mono. So now by this, what is H2O? It's water. But what's its fancy name? Dihydrogen. So that would be dihydrogen because I have 2, H2, monoxide. That tells me 2 hydrogens, 1 oxygen. Notice none of these have metals. These are all non-metals and hydrogen. So we'll practice a couple of them. So we got CO2 already, right? So CO2 is carbon dioxide. And you can have carbon monoxide, carbon dioxide. You can even have carbon trioxide. And this is the reason, because there's different numbers of them, this is the reason you have to use number prefixes. So what's CBr4? Carbon. What is 4? Tetra. And then first part of the second element plus IDE, so that would be bromide. Carbon tetrabromide. So N2O4. Dinitrogen. It's hard to say it this way. Like you have to kind of get used to just seeing it this, but dinitrogen just means 2 nitrogens. And you always say that if it's out front. And then, tetroxide. So if you use oxide, you drop that vowel if there's one in it. So NH3, this is ammonia, but NH3 would be called what? N is? Nitrogen. Tri. So it's not hydroxide because remember that's the OH. But so you use the first part of hydrogen plus IDE. So what do you think it sounds like? It's hydride. So that's nitrogen trihydride. Now hydrogen you haven't used in an ionic naming, so that's why it sounds very strange. Because remember we've done bromide, fluoride, iodide when we were doing the ionic, because it's a metal and a non-metal. So you've kind of seen the oxide bromide stuff, but you really haven't seen hydrogen as a second element. So that's the one. That's why people are like, I don't know, I've never heard it. And it's just because we haven't really used it. So if you see the hydrogen second, it's hydride, okay? But remember, like with this one, hydrogen's out front, so you don't use hydride, you just call it what? What's H2O2? Its common name is peroxide. That's hydrogen peroxide. But you would call it by its fancy name, it's dihydrogen, because you always use the whole name of the first element. And then O2 would be dihydrogen dioxide. So the last one, NF3. 3 is? Nope, F. What's F? Fluoride. Yep, so trifluoride. I don't know, but for some reason people still want to think that fluorine is FL, which is Florida. It's not. Actually, there is no element with FL. That's a state abbreviation. So I see that all the time. So it's just fluoride. And remember, it's UOR, like not OUR, because that's flour. Those are like 2 common misspellings and then common abbreviation oddities that I see. I'm like, why would they do that? But, all right, now it's gone again. Okay? So now we can actually tell the difference. We can tell them apart. We can tell, well, which one's ionic and which is covalent, and how do you name them? So if you're given an element formula, or if you're given a compound formula, or if you're given a compound name, you can identify if it's ionic or covalent, and you can identify what its name is or get the formula from the name. So here's like the little flow sheet, the flow sheet. So we're going to practice. So 1, I need to know, is it ionic or covalent? Okay, and the trick is look at the first element. So whether you have a name or if you have a name or you have a formula, it doesn't matter. Look at the first element in the name or the formula If the first element is a metal, then you know that you have ionic. Okay? So you always have your periodic table, so you don't have to memorize what things are. But how do you tell a metal from a non-metal? You look at the zigzag line, right? So you just look at the zigzag line. If the first element is on the left, I know it's ionic because those are all metals, except hydrogen. It really belongs over here, okay? If the first element is a non-metal or hydrogen, then I know it's covalent. So if it's non-metal and hydrogens included in this, then I know it's covalent. Okay, so if it's ionic, and it includes iron, chromium, or copper. If there's iron, chromium, or copper, then I know I have to use number prefixes. I know then I have to use the Roman numeral, right? So I'm going to end up with like iron with the +2, or I have iron with the +3, because those can have a different number. So I know in doing the naming, I'm going to have to put that Roman numeral between the metal and the non-metal. If not, if it's group 1, 2, or 3, so if it's like lithium, sodium, potassium, beryllium, magnesium, calcium, or aluminum, because that's the only one really in group 3. So if it's the first 2 columns or aluminum, then I know I just name it. No Greek prefixes, no Roman numeral. It's just like sodium chloride. So I just use the whole name of the metal, first part of the non-metal, plus IDE. Right? So we can have things like Al2O3. We can have things like NaCl. Whereas up here, we can have FeCl2, we could have FeCl3. That you would have to be able to tell the difference between them. If it's all nonmetals, then I know it's covalent. Nonmetals and hydrogen, then I know it's covalent. And here, I always use the number prefix. So if you have something like NO2, CH4, I'm thinking like H2O. So anything like that, then I know that those are covalent because there's no metal. Only nonmetals and hydrogen. So that's really the trick. The trick is look at the first element. So we're going to do these ones. You tell me first, is it ionic or covalent, and then tell me the name. So C2H4, is this ionic or covalent? How do you know? Okay, where's the metal? So what's the first one? So C2 is? So C2 is carbon, hydrogen is H. Remember, so if it's nonmetals and hydrogen, then I know that that's covalent. Right? So this is a nonmetal. It's really the trick. Just look at the first element. So the first element's carbon, so on to the right of the zigzag line. That's how I know it's covalent. What about the second one? Right? Because this is a metal. This is a metal, so I know it's ionic. What about the next one? Nitrogen. Where's nitrogen? That's a nonmetal. So I know that that's covalent. What about CaO? Right? Because this is a metal. CO? Covalent. Right? Carbon is a nonmetal, so I know it's covalent. PO3? Covalent. CCl4? Because carbon, again, nonmetal. S2O6? Covalent. I was just trying not to trick you into getting every other. And then the last one, NABR. Ionic, because see, this one's a metal. That's ionic. So you can see that's really the simplest way. Just go along. Doesn't matter if I gave you the name or the formula. Just look at the first word Or look at the first element in the formula. If it's a metal, it's ionic. If it's a non-metal, it's covalent. Okay? And 99.9% of the time you're right, unless you have ammonium. That's the only time that doesn't work. Okay? So if it's covalent, do I use number prefixes or no? Does covalent, does C2H4, do I need number prefixes? Yeah. Yes. If it's covalent, I have to use what I call the number prefixes. So I have to use mono, di, tri, tetra if it's covalent. So that means C2H4 is dicarbon tetrahydride. Right? So you take hydro from hydrogen and add IDE. You have to use those Greek number prefixes if it's covalent. So let's go down and do this one. So what's this one? N2O2. Dinitrogen and dioxide. Yep, dinitrogen dioxide. So then go down here. Let's do this one, CO. It's not cobalt, it's capital C, capital O, so I know that that is carbon and oxygen, so that is, yep. Go back. No. Okay, nope. Last two, come here. Okay, there's carbon. Oh, it just went away. That is carbon monoxide. Right? One oxygen, one carbon, I don't have to put mono, but since the second one is only one, I have to have mono there. So CO is carbon monoxide. You've probably heard of that. So PO3, it's also covalent. So that is, what's P? Phosphorus. So phosphorus. And then what? Yep. And you keep the tri, you don't drop the I. I don't make the rules. But CCl4. Yep. 4 Cl's would be tetrachloride. Yep. Carbon tetrachloride used to be used as like a fire extinguisher. It's really heavy and it would like smother a fire. But when it gets hot, it breaks down and makes chlorine gas. So they found that that wasn't so great for people. So they don't use it anymore. But that's like one of the first uses there because it's super heavy. So they would just drop it on a fire and it would like take all the oxygen away from the fire and it would go out. All right, what about this last one? So here's the last covalent one. Then we're going to go back and do the ionic. So S2O6. S2. Disulfur, right? You use a whole name, even though that sounds strange. Disulfur. And then, what is 6? Hex oxide. Disulfur, 2 sulfurs, hex oxide. Okay, so now let's go back and do the ionic. So K3N. Yep, potassium. Potassium what? Nitride. Super easy. No number prefixes, remember? So it's just like sodium chloride. You don't have to use number prefixes. That's the only way potassium and nitrogen will combine because they transfer electrons. So then what is CaO? Yep, calcium oxide. And then the last one, NaBr. Sodium bromide. Nope, because it's ionic. So just put yourself a note. If it's ionic, no number prefixes. So potassium nitride, no number prefixes. Calcium oxide, just whole name of the metal, first part of the non-metal plus IDE. That's all you have to do. So I gave you this, right? So remember, you did this front page, right? Didn't you guys do all the ones on the front? Yeah. Okay, so now the back. So the back page, let's see, the back page. What did you do? So I know I saved that. Okay, so again, so if you missed any of these ones, if you want to go back and like practice them again, I do have this posted. This is actually posted in Moodle. So it's just listed as the practice sheet. And so we went through and did all of these. So Amber, like, you can go back and practice this one. The answer sheet is posted in Moodle. So down here, so you tell me, what is the rule for naming ionic compounds? You use what? Yep, okay. So in this, whole name of the metal plus then what? Plus IDE, like sodium chloride, right? Whole name of the metal, first part of the non-metal plus the IDE. So example, Mg3N2, what would I call it? Yep, magnesium nitrate. No number prefixes needed. That is the way that they combine. If I want to go from the name to the formula, like calcium iodide, what do? Like do this in like the two-step thing. So what do I write first? Calcium iodide, what would I put? Yeah. Ca. And what would its charge be? +2. How do you know? It's the group number, right? So remember the metal, it's the group number. So that's the group number. And then iodide, what's that? What's its symbol? I. And then what's its charge? -1. And how did you know? Right. So I figured out that charge because it's 8 minus its group number. So you list the symbols, assign the charges based on those rules. Now what do? Then you do the swap. So what this is going to tell you then, so the charge on the calcium tells you how many iodine, the charge on the iodine tells you how many calcium. So that's what I mean by the swap, and that's how you figure out the formula. So the final formula ends up being what? I2. Right? If there's only one, I don't have to add a 1, like calcium, because the -1 of the iodine tells me 1 calcium. So when I do the swap, it's just CaI2. Okay, so to do the opposite, so you write the symbols, assign the charge to each, to the metal and the non-metal, do the swap. Charge on the metal tells you how many non-metals, the charge on the non-metals tells you how many metals, and then if you can, simplify. And do you remember what I mean by that? So when I say, if they came out and it was like Ca2O2, if they were both even numbers, simplify it to CaO. Okay? It doesn't happen very much, but if you did yours and you notice, oh, they're both 2s or they're both 3s, you could simplify that. All right, so now the rules for naming covalent compounds. So unlike the ionic, what would you say? You're going to use okay, so I have to use number prefixes. Except yes. So if element 1, well, better way of saying it, first, then you have no mono. I have to use a number prefix. What else? So how am I going to name this? Like N2O4. What do I use for N? Okay. So by that, I know that I have to use the whole name of the first element. Then another number prefix. And do I use the whole name? Then I'm going to use what? So O4 is what? So I use first part of the second element plus IDE. Dinitrogen tetroxide. So what is phosphorus trifluoride? How would I write the formula? What's phosphorus? And since there's nothing in front, then I know there's only one. So then trifluoride would be yep. So that would be PF3, phosphorus trifluoride. If the first element's a 1, you don't have to put mono. Okay, so here's the last one. So in this, I'll give you a couple minutes. Okay, so in this, from the formula, tell me the name and tell me if it's ionic or covalent. It might actually be easier if you just go through and identify ionic versus covalent first. Then, from the name, give me the formula. From the formula, give me the name. This one throws in some polyatomics too. And a transition metal. So here's this one. So in the first one, so if you look at the name and you see the first word is iron, is that a metal or a non-metal? It's a metal, so that means this is ionic. Right? So this is a metal. That's how I know it's ionic. So if I look at if I look at Ca parentheses NO3 2, what is calcium? It is a metal, so I know that this is ionic. Okay, if I look at S4O2, what is S? It's a nonmetal, so I know this is covalent. Potassium nitride. Potassium is a metal, so that means this is ionic. PBr3. P is, so that means it's a nonmetal, so this is a covalent. Pentanitrogen. Nitrogen is a nonmetal, so that means this is a covalent, right? Hopefully everybody's gotten those. So Cu3P. Cu is a metal, so this is ionic. And the last one, ammonium. So what do you know about ammonium? It's tricky because ammonium is a what? Anybody remember? It's a polyatomic ion. So what is that? It's going to be what kind of a bond? It's got to be ionic. So this is a polyatomic. And because of that, I know this is ionic. So polyatomic ions always form ionic compounds because they exist as ions. Okay, so now, change color. Let's go to the blue. So now in this, when you go to do the formula from the name or name from the formula, name to formula, you take iron, and it's iron 3. What does iron 3 tell you? That it's a +3. Sulfide is sulfur, so that is in group 6, so it's a -2. So now I know, I wrote my elements, I assigned the charge, now just swap them. So that means that now I have Fe2S3. Done. Okay, so what about the next one? The next one's ionic. I gotta just go from the name to the formula. This one's pretty straightforward. What is that? Calcium nitrate. Calcium, whole name of the metal. Now when you have, I put down there, if you have a polyatomic, you just use the name of the polyatomic. So remember there are 7 of them. I gave you a list of 7. I'm sure you're gonna want to put those on your note card, right? So you wanna remember like NO3 has a negative charge and it's called the nitrate. So this is calcium nitrate. So S4O2, what would its name be? S4 tetra. Tetra, sulfur, and what else? Dioxide, yep. So if I have something that's ionic and it's potassium nitride, to figure out the formula, I have to put down the symbols. Potassium is a K. Come on, stop doing that. Potassium is K, and its charge +1. Nitrogen is an N, and the charge is -3. So remember, the metal, it's its group number. The nonmetal, it's 8 minus its group number. Now I just do what? Swap them. If it's ionic, I now just swap them. So now that's K3N. PBr3 is covalent. So what's its name? Phosphorus. Yep, tribromide. Pentanitrogen trihydride. Sounds super crazy, but pentanitrogen means how many nitrogens? 5. So this is N5. And then trihydride means 3 H's. H3. C3P, ionic. So in this name, there's one thing I have to do that's kind of weird and special. Because it's copper, what do I have to include? The Roman numeral. So that means that I've got to figure out what the charge on the copper is. So if I have Cu and a 3 in the P. So what's the charge on phosphorus? -3, right? Because it's in group 5, so 8 minus 5 tells me it's a -3. Do you see those are the same? See that the copper is a 3 and the phosphorus is a -3? So that means if I have 1 phosphorus, what's the charge on my copper? It's 1 and 1, so that will be a +1. Does everybody remember? So this, it's like doing the reverse swap. So see, if the number on the copper matches the charge on the nonmetal, then I know that the other two are going to match as well. So in that one, that means that this is copper what? Copper 1 phosphide. Okay, and then the last one. So the last one's ammonium phosphate. So you got to look at the polyatomics. Ammonium is what? It's NH4 and has what charge? Ammonium. It's one of the 7 is the ammonium. It's the only positively charged polyatomic, right? So it's NH4 what? Plus. So it's got a plus. And then phosphate. What's the phosphate? So phosphate is PO4 with the -3. Okay? So now I've got those. How do I swap these? What do I have to make sure I include? The parentheses. So see that the ammonium is a +1. The phosphate's a -3. So they're not the same. So when I swap them, which one gets parentheses? The NH4 does. So I'm going to have to go parentheses, NH4, 3, and then PO4. I don't have to put parentheses because it's only a 1. Okay, did anybody get all those right? Okay, well, these are good ones to kind of practice. Like, these are good examples of ones to practice. Picking out ionic versus covalent, naming ionic, naming covalent, and then just going back over those transition and polyatomic ones. I will save this and post it. So this will be the answer key will be posted in Moodle. So if you go back and look at this one, you can do some more practicing them, just reviewing. So I'm just going to hold that.